Welcome back to our series on probability theory. I'm Mark Ledbetter. This is lecture video 46, part A, and we are entering into a discussion about multivariate independence, or the independence among many or several variables. In the last section, we talked about bivariate transformations. Mostly, we talked about the transformations of continuous random variables. And we introduced the bivariate or inverse transformation theorem for one-to-one functions. And with that, we did some examples, and one of the distributions that we ended up deriving using these transformations was the Cauchy distribution, the standard Cauchy distribution. And another was the beta distribution, which were new distributions for us. And then we did several examples and gave several results that are extremely important, especially if you're going into next semester mathematical statistics. These results from sections 1 and 2 are very important. You need to have those listed somewhere so you can readily know these transformations. They're very important. We also talked about how to do discrete transformations where there's no real theorem. You just have to use some logic and work it out individually. So in this section, our overview is 5.3 in the book. We're going to introduce the topic of the different random variables being independent and give a kind of soft introduction into the more technical aspects of this. We're going to define a random sample and talk about some of the properties of a random sample. And then we're going to, and this is again very important for next semester, and then we're going to give some theorems. One of them is on the expected value of some key sample quantities, such as the x bar, which is the sample mean, the sample variance, and the sample standard deviation. We're going to do a few proofs, and then we're going to look at more theorems for the expected value of a product of functions of random variables and the mean and variance of linear combinations of independent random variables, and then do some examples. So let's get started. So we are, again, performing, in this section, we're going to explore performing several random experiments. Another way to think about this, which is equivalent to this, I'll change to blue. So equivalently, instead of performing several random experiments, we could perform one random experiment several times. So each trial has one result or measurement that can be considered a random variable. And in other words, we obtain one random variable and one result from each experiment, and thus we obtain a collection of many random variables from many different experiments. And these experiments are performed in such a way that the events that are associated with any one of them are independent of the events that are associated with all the others. So this implies that corresponding events are probabilistically independent. Okay? So they are probabilistically independent. If you recall from earlier, if x1 and x2 are discrete, and we'll start with discrete because it is a simpler case here, and we can use equal signs a lot easier. If they're discrete random variables and they have PMFs, probability mass functions, f1, f2, f1 of x1, f2 of x1, then the probability that x1 is equal to little x2 and x2 is equal to little x2 is equal to simply the probability that x1 is equal to x1, little x1, and x2 is equal to little x2. And since they're discrete, this is equal to the product of their PMFs. And since they're discrete also, this becomes the joint PMF, where x1 is in S1 and x2 is in S2. So we can take a simple example here and talk about rolling one die 2 times. And then we can roll 2 dice simultaneously or once. Okay? So these are identical when it comes to probabilistically. Okay? So there's no difference. Because they're independent, the answers are going to be the same. Okay? So for the first die, we'll let f of 1, x1, be the PMF, and that is going to be 1/6 because there's 6 sides on the die, and those sides are labeled 1 through 6. And so x1 can take values between 1 and 6. And then f2 is also 1/6, and x2 again takes, f of x2, I hope I said, is 1/6, and then x2 can take values between 1 and 6, including 1 and 6. And again, because x1 and x2 are independent, the joint PMF of x1 and x2 is given as f of x1, x2 equals the product f1, x1 times f2, x2, and 1/6 times 1/6, which is 1/36, and we can't forget our support, our joint support or range of x1 and x2. So we used earlier in the semester, I believe back in chapter 1, we talked about the multiplication rule for events. And we said that for any two events, the probability that event A and B occur either simultaneously or at the same time or together is the probability of A times the probability of B given A. Now in this is one way to write this. If you remember that we solved the equation for the conditional probability of B given A for the probability of A and B. We could also use the probability of B times the probability of A given B, and that also is the probability of A and B. But in this case, what we did was we solved the equation for the conditional probability of A given B, right? So there's two different ways that we can solve for this. So if A and B, if you recall, if A and B are independent, then the probability of B given A, since B is independent of A, it doesn't matter what happened with A, what result occurred for A, it's still just the probability of B. Now, if we substitute in the probability of B in place of the probability of B given A into this equation here, we end up with the probability of A and B equals the probability of A times the probability of B. And again, this is only true when A and B are independent. Otherwise, we have to use one of the conditional probability rules. Okay. Now we're wanting to look at the pattern, okay? And we're going to introduce a third event. We're going to call it C. And C is going to be independent of both A and B. So it's there's mutual independence here. And so the probability of A and B and C is equal to, what we're doing here is we're going to group A and B together and treat them like A1 or A star, let's say. And so this is equal to the probability of A and B times the probability of C. And that's using 2, which is here above. Okay. Now, as I mentioned, we can group this, and we can see that we can use the conditional, we can use number 1, the conditional probability statement of the, or the multiplication rule. And so we have the probability of A and B times the probability of C given A and B. But since C is independent of A and B, this simply reduces to this. And then we already know that the probability of A and B is the probability of A times the probability of B, and now it's times the probability of C. And so we find that the probability of and so we found that the probability of A and B and C is equal to the probability of A times the probability of B times the probability of C. We could do a similar thing and find out that we have this relationship for 4 events that are independent if D is also independent. And we could keep doing that. And with this, we see a pattern. And this is not a formal proof, though. So we can see what happens by looking at this pattern. Now, we haven't proved anything, but it's obvious that this is what occurs, that we can continue expanding this. So we did a formal proof of this earlier in the semester, but we used induction. And that is what you would have to do to prove this formally. And induction requires all three steps. And we're not doing those steps. We haven't done step one really very well. We did do it earlier up here, but we need to do all three steps and formally, and then we can say that we have proved this. So right now we have not proved it. So the method, again, the method of seeing a pattern is not induction. It's simply intuition, all right? So please don't confuse that with formal proofs. So now we come to the definition of something that's extremely important in statistics. If you've taken an introductory statistics course, then you've heard of a random sample. So far, we haven't been talking about samples. We've been talking about populations and distributions and random variables, okay? So now, if we have a definition for the random sample, that is that random variables x1, x2, all the way up to xn will form a random sample of size n from a population with a distribution f of x. Now, we're no longer talking discrete. This could be for discrete or continuous, okay? So random variables x1 to xn form a random sample of size n from a population with a distribution f of x if the following two properties are met. x1, x2, xn are all independent. 2. The marginal PMF or PDF of each x sub I is f of x. So they're all from that same distribution. If you're taking a random sample from a population, if it's a single population, it makes sense that they all have the same distribution function, f of x. And so these two properties make it a random sample. So we say that x1 to xn are IID, that's independent and identically distributed. And we've talked about that before. So they're IID f of x. And the joint PDF or PMF of x1 to xn, of all of these, is going to be given by the product of f of i's. So this symbol here, the large pi symbol, means multiplication or product. So what we're doing here is we're taking f of 1, x1, times f of 2, x2, all the way up to f of n, x sub n. Okay? So if we're given a random sample, the set of x1 to xn, we're interested in the following quantities: the sample mean, the sample variance, and the sample standard deviation. So the sample mean is x bar. This can also be written as the sum of xi over n. I wrote it out in long form here because that's what we're probably going to use here shortly. Then the sample variance, s squared, is given by the sum of xi minus x bar, quantity squared. So we're taking the difference of every value from the sample mean, and we're squaring that distance, and then we're dividing that by n minus 1. Okay? And next semester we'll find out why we're doing that, the n minus 1 instead of n. And this can be written, these are equivalent. These are exactly the same equation, just rearranged using some algebra. We can write that using the computational formula. This is the one that the computer and calculator uses. N times the sum of x squared minus the sum of x quantity squared over n times n minus 1. And then the sample standard deviation is simply the square root of the sample variance. So the theorem that we have here is that the expected value of x bar is equal to mu. This is the population mean, or the mean of the distribution f of x. And then we have the variance of x bar is given by sigma squared over n, where sigma squared is this is the variance of the population f of, which is given by that function f of x. And then E, the expected value of S squared, is equal to the population variance, or the variance of f of x, the distribution. And then finally, the variance of S squared is given here in this equation, and we're not going to prove this, and I don't think we'll use it this semester. Well, we won't use it this semester. We might use it next semester. So I wanted to give this to you in case we need it at some point. All right. So let's look at the proof of A. This is a very simple proof, and so we're going to say the expected value of x bar we substitute in for x bar. And so that's x1 plus x2 plus x3 all the way up to xn, and divided by n. Well, n is a constant, so I can rewrite this as 1 over n times this quantity. And for the expected value, if I have e of ax, that's equal to a times e of x. That was one of the theorems that we proved. So I can pull the constant out in front of the expectation. We also learned that the expected value is a linear operator. That means you can think of this as like distributing it across the plus signs. And so this becomes 1 over n times the sum of e of x1 plus e of x2 on up to e of xn. And this is mu. They're from the same distribution, so the expected values are the same values. So this is, and there's n of these. So we have n times mu over 1, or times 1 over n. The n's cancel, and we end up with mu, which is exactly what we would like. And so e of x bar is mu. Therefore, x bar is unbiased. Bias of, let's say, theta hat, some estimate of some parameter theta. It could be any parameter of the population we want. So we're using theta just as anything. This is equal to e of theta hat minus theta. And if this is 0, then theta hat is unbiased. If it's positive or not equal to 0, then it is biased. So if you solve this, if this is equal to 0, if we solve this part here, then we'll see that this implies that e of theta hat is equal to theta. And that's exactly what we have here. So x bar is unbiased, e of x bar minus mu is 0. And again, we're using the fact that x1, x2 to xn are mutually independent and identically distributed. In other words, they're a sample from the same population, okay, or a random sample from the same population. So that's it for this video. Please don't forget to scan and upload your lecture notes before midnight, the date listed in the course calendar. If you have questions, come to virtual office hours. If you need an answer before you can make it to virtual office hours, then please email me. But I'll need you to send me a picture of the problem and a picture of your work so far so I can see how you're approaching it, and I don't have all the problems memorized, so I might not know which problem you're talking about. So please take care of yourself and stay safe, and I hope to see you next time.